Next, we'll be taking a look at the notation used to denote derivatives and also the units of a derivative of a function. So two important things to be aware of. So the first one, if we have a function f of x, so this is a function, then we said that its derivative is denoted with a prime, so this is the derivative. So this is called Lagrange's notation. So an alternate notation for the derivative is due to Leibniz. So the Leibniz notation, we would say dy dx. Right, so this would represent the derivative function, just like y represents f of x. So the two notations can be used together. We can say y is equal to f of x, then we can say dy dx is equal to f prime of x. So this would be the Leibniz notation on the left, Lagrange notation on the right. So if you see dy dx, it simply represents the derivative, just like f prime of x represents the derivative. It's the same thing. One thing to be aware of is that dy dx itself should be treated as its own unit or its own symbol. So you can't cancel out the d's. You can't say, well, this is equal to y over x. You can't multiply both sides by x. There is a slight exception. We can sometimes we can get away with treating dx and moving it around and having the dy separately from the dx, but we'll get into that later. For now, just think of this as one, glued together structure that is always all or nothing, right? So it's dy dx just represents the derivative, that whole thing. Now, where does this come from? Well, we use delta to represent a finite change. So this is the difference between two discrete points. But in the limit, as those 2 points go to 0, you have something that is an infinitesimal change, which of course, when you just take the limit as delta x goes to 0, delta x, you get 0. But the ratio does not have to be 0, right? So remember, the limit definition, we had f prime of x was the limit as h goes to 0 of f of x plus h minus f of x over h. You can alternatively write this as the limit as delta x goes to 0 of delta y over delta x. So for any finite delta x, you have a finite change in y over a finite change of x. If delta x is equal to 0, the change of y will be 0, and you get 0 over 0. But when you approach 0, the ratio of the change of y over change of x approaches the value of the derivative. And so we say that the change of y and the change of x as in the limit as delta x approaches 0. So as delta x is so finely infinitesimally small, the ratio of delta y over delta x goes to a certain value known as the derivative, or the instantaneous rate of change. So we say this is dy over dx. So the motivation behind this is that dy over dx is an infinitesimally small change of y divided by an infinitesimally small change of x. So dy and dx by themselves are infinitesimally small, but the ratio is what's important, right? When we looked at the linear function f of x is equal to 3x plus 7, it's a line with slope equal to 3. That ratio of delta y over delta x is always equal to 3. So as we shrunk it down, that ratio is equal to 3, even though as when we get smaller and smaller and smaller, delta y and delta x become infinitely small. It just happens to be that delta y is always 3 times larger than delta x. So that's why that ratio comes out. In a variation of Leibniz notation, you might see something like this. Compute d by dx of 3x plus 7. So here, d by dx is sometimes called an operator. So it basically means take the derivative, or compute the derivative of what follows. Right, so d by dx of something. Right, so if we think about dy dx, so this is kind of the justification. If we take y and kind of knock him down here, we get d by dx of y. So we think of that d by dx in this case as acting on the function y, or we just slide him over a little bit. We say d by dx bracket and then y, and then of course you can replace y with the actual function. So if you want to say, so it's kind of like this. Y equals f of x, dy dx is equal to f prime of x. So this would be, y is equal to 3x squared plus 7, and then dy dx is equal to 6x. And I didn't work this one out, but that's what you would get. So you would read this: the function f of x is equal to 3x squared plus 7. Its derivative, f prime of x, is equal to 6x. So it's almost two separate statements, two separate sentences. By using d by dx of something, we can just say this in one sentence. The derivative of 3x squared plus 7 is equal to 6x. So you would just say that d by dx of 3x squared plus 7 is equal to 6x. So these are just ways of writing the same thing. The derivative of this stuff, 3x squared plus 7, is equal to 6x. So here I said that the derivative of 3x squared plus 7 is equal to 6x using a single sentence, whereas up here it took me two sentences. It took me one sentence or equation to say that the function is 3x squared plus 7, and then a separate sentence or a separate equation to say the derivative is 6x. Here it's just the derivative of 3x squared plus 7 is 6x. So that's the notation. The three, we have f prime, y, dy dx, and then the operator notation d by dx acting on something. Units. Always important to know what your units are. So we've kind of just looked at derivatives kind of abstractly, thinking about functions and their graphs and the changes. But usually these functions represent things like the number of inches of rain that fell on the 10th day of the year, or the pressure, X meters below the surface of the ocean, etc., etc. So the input has a unit and the output has a unit. X has a unit, Y has a unit. So what about the derivative? Well, let's take a look. So Y is equal to f of x. So I'll use a notation just for a shorthand that I use just a few times when I'm talking about units. So I'll use this square bracket to represent the units of x. So if x is in meters, we would have the square bracket around x and say is equal to meters. It's just a little, it's context dependent. So if you're talking about units and I write something like x is equal to meters, I'm saying the units of x is equal to meters, maybe. Y is equal to kPa, kilopascals. It's a unit of pressure, 1,000 pascals. The units of y are kilopascals. So I'll just use these square brackets for the moment to denote the units. So what are the units of f prime of x? So the units of f of x would be kilopascals. What would the units of f prime of x be? Well, recall that f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. Well, the limit doesn't really change the units. If you have units of slugs for any value of h, when you take the limit as h goes to 0, the units are still going to be slugs, or whatever units you have here. So really the units of the derivative are the same as the units of this difference quotient. So the units of f prime of x have to be the units of the difference quotient, which is basically delta y over delta x. Well, the delta y has units equal to the units of y, and delta x has units equal to the units of x. So this is just the units of y over the units of x. So basically, the units of the derivative, the units of dy dx, or alternatively the units of f prime, are just the units of y divided by units of x. The units of the y variable divided by the units of the x variable. So if your function is p of x, let's say x is meters below the surface of the ocean, and P of x is the water pressure, or the hydrostatic pressure. So it's the hydrostatic pressure, probably the correct way to refer to it. So it's basically the pressure at that depth in, let's say, kilopascals. P prime of x, the units are going to be kilopascals per meter. The units of y divided by the units of x, kilopascals per meter. That makes sense because what it represents is it's a change in the amount of pressure per change in additional depth below the surface. And we'll talk about this a little bit soon when we talk about physical interpretations of the derivative.